Hi, this is Scott Wilkinson, host of Home Theater Geeks. In episode 246, I chat with PSB founder and chief engineer Paul Barton about his new Imagine T3 speakers. So stay tuned.
Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Home Theater Geeks is provided by CacheFly at CACHEFLY.com.
This is Home Theater Geeks with Scott Wilkinson, recorded March 5th, 2015. Episode 246, PSB's latest speakers. This episode of Home Theater Geeks is brought to you by SmartThings. SmartThings lets you monitor, control, and automate your home from wherever you are using your smartphone. Right now, SmartThings is offering Home Theater Geeks listeners 10% off any home security or solution kits and get free shipping in the U.S. when you go to smartthings.com/twit and use the offer code TWIT at checkout. Hey there, Scott Wilkinson here, the Home Theater Geek and editor of avsforum.com. This week's guest geek is Paul Barton, founder and chief designer for PSB Speakers, talking about his latest developments. Hey, Paul, welcome back to the show.
Yeah, thanks for having me.
Always glad to have you here.
I think we've done a few of these shows in the past.
We have. I think this
might be number 4.
I think it's 3 or 4, something like that. But it's always great to have you on because, you're like those of us who watch the show and me, who is the host of the show, definitely Home Theater Geeks. I mean, you're a serious geek and a musician to boot. So those two things together make for a potent combination, and I'm sure we're going to have a great conversation today.
Yeah, I'll be able to tell you about the latest and newest developments on both the speaker and the headphone front.
Yes, indeed. And there's some great news on both of those fronts. Now, before we get started, I just want to make sure that everybody knows that those of you who are watching live at our new time, by the way, 2 p.m. Pacific, 5 p.m. Eastern time, on live.twit.tv, can post questions in the chat room. You can go there from live.twit.tv or just point your browser to irc.twit.tv and post some questions for the chat room. I monitor that, and I'll pass along as many as I can. It helps if you put my screen name in your message, which is my full name, Scott Wilkinson, no space, because then it shows up in a different color on my screen, and it draws my eye more easily to it, and I can notice it better. Okay, so Paul, you and I have been friends for a long time now, and I'm very proud to say that. And I've always loved your speakers. PSB speakers are always at the top of my list of recommendations. But I must admit that the way that you've named your speakers has always been just very slightly confusing to me. You've got all these different names: Imagine, Image, Synchrony, so on and so forth. But I think you told me offline that the new speakers that we're going to talk about today help address that problem, among others.
Well, yes, it was confusing, and we made a decision to simplify it a bit. We have now basically the Alpha series. We have the Imagine series, which covers right from the entry level in a X box, we call Imagine X, right up to the T3, which we'll be talking about today. So that just covers the whole gauntlet of models. The Synchrony name and series has been discontinued, but the T3 sort of continues that higher echelon of performance that we aspired to in the Synchrony series. So nothing's been lost, except we made things a little simpler. Of course, we also have custom products, which is in our CS series, Custom Sound series, which we'll touch on some other time. But yes. I think we should focus on the two items that we talked about yesterday.
Yes, exactly. The Imagine T3 is a new flagship product for PSB, and we have a picture of two of the items, two of the models from that series in the family of Imagine T3. We have the, if we can take a look at that, the floor standers, the towers, and the center channel, which I think you said was called the C3, right?
That's correct. And this complements the other models in the Imagine series. We have an Imagine S, which is a surround. It can be used with this series. It can also be used with the Imagine T2, a less expensive, smaller footprint version of this tower you see in front of you. We also have an Imagine T, the whole series, a B, a bookshelf, center channel, a smaller one. So it's a full home theater complement of products that can be configured in any way you would like. And even with some of the new models we're doing in custom sound, adding some of the new series, which we'll be introducing very soon, as the ceiling speaker Atmos, then you'll be able to do a full home theater Atmos system with Imagine products.
Oh, excellent. Can't wait to hear that.
Yeah.
So the previous flagship was the Synchrony 1, and you told me yesterday that you've made some improvements. Can you sort of outline what those are?
Yeah, if anyone were to ask me, what would I do to improve the performance of any loudspeaker? Given a model, what would be the challenges to raise the bar on that model? Well, Synchrony 1 being our flagship, I had to look at all aspects of the performance and see what could be done to raise the bar. And there were four things that I concentrated on. One was the overall sensitivity of the speaker. It's about 1.5 dB more sensitive than the Synchrony 1. Another thing that you would want to do is increase the capability dynamically. So not only is it more efficient, the surface area of the drivers, in the Synchrony 1, they were 6.5-inch drivers. On the Imagine T3, they're actually 7-inch drivers. The mid-range on the Synchrony 1 was a 4.5-inch driver, and the mid-range on this T3 is a 5.25-inch driver. So we've significantly increased the piston area of the output of all the drivers so that they don't have to move as far, which means that when they do move as far, they will actually play louder. That gives the speaker, well, actually, it attributes somewhat to the sensitivity increase, but other things helped to do that was a decrease in the mass of the cone, and I'll explain that in a minute. But the fact that the piston area goes up means that the sensitivity is increased slightly, but also the dynamic capability of the loudspeaker. I don't know if people out there are aware, but one of the weakest links in today's source material being reproduced with the dynamics that are available is the most challenging thing for a loudspeaker. Dynamic range is the buzzword for the future because frequency response is attainable. We can control directivity. We have much better understanding of the speaker-room interface. But in real life, one of the biggest challenges is real-life dynamics. And so anything that can be done to increase either the sensitivity and in parallel, the piston area or the output capability of a speaker is always a good thing.
Now, when you say dynamic range, before you go on, when you say dynamic range, I think we must qualify that by saying it depends on the type of music and the recording that you're listening to, because an awful lot of popular music is mastered and released with a very limited dynamic range on purpose to make sure that you can hear all of it in the car or over the radio or whatever. So in some cases, a wider dynamic range isn't necessary. Of course, when you've got a recording of a classical symphony or something that's been recorded in a way that produces very wide dynamic range, particularly if you're using more than 16 bits, as we know, high-res audio is a hot topic these days, then you're right. You absolutely need that. The speaker needs to be able to reproduce that higher dynamic range.
Well, yeah, I agree. On a lot of commercial recordings, dynamic range is controlled just by virtue that they know the systems they'll be played back on may not be capable, or the environment that they're being played back on doesn't accommodate this wider dynamic range. But high res is becoming more and more popular and more available, especially with downloads off the internet, streaming media, etc. And some of this recording material is straight out of the recording studio. So, and it's at up to 192 kilobytes and 24 bit.
Yeah, kilohertz, actually.
Kilohertz, sorry. What that means is that there's no compression. That I'm hoping that what the musician intended in the dynamics and the sound spectrum of his recording is maintained, and probably the most pristine when you use a high-res recording. And home theater is also moving in that direction with Dolby High Def home theater, and I think DTS has a similar version. So that I don't think we want to cheat the producers from allowing from the medium allowing their music and their productions to be enjoyed by the audience in the fullest way.
Mm-hmm. So I couldn't agree more. Absolutely.
I think dynamic range reduction is a necessary evil in some applications, but I wouldn't want to personally restrict PSB based on that fact that there is some compression that goes on a lot of commercial recordings, especially if it's compressed, etc.
Right. Okay, so you said greater sound output, greater dynamic range. Those are two.
Right. The other thing you would want to do is reduce distortion. And a little later on, I think we have some slides to show some of the things that we've done in the speaker to try and reduce distortion. They're not rocket science. They're just well-known techniques for reducing distortion, and we've applied as many of those features and hopefully optimize them with computer optimization software and finite element analysis today. One of the biggest challenges when you learn a technology is, okay, we know the technology exists, but how do we optimize it? What trade-offs do we make if there are any to be made? And that's basically, as time goes on, when I'm designing loudspeakers, I'm not necessarily using anything new, but I'm trying to make it better because things get more optimized and some of the parameters are better understood.
Mm-hmm.
Let's see, I gave you 3 points. The other thing that you try and do with a loudspeaker is improve its directivity, so that anywhere you sit or any kind of environment the speaker may be in, because speakers will end up in environments that are either reverberant right down to being very dead. So in a dead environment, what's going on off axis isn't that important. But in a very live environment, what's going on off axis is very important. So I tend to polarize my designs around understanding what the directivity of the loudspeaker is, trying to make it as constant in all directions so that even if it is in a live room, the sound power, which is something you hear more of in a loud room, is also very well balanced along with the direct sound coming from the loudspeaker. So again, that's something that has been optimized just to another degree on the Imagine T3.
Mm-hmm. Regarding directivity, I've always thought that has, it's at least in part dependent upon the frequency, that low frequencies tend to spread out and be more spherical, much more than high frequencies coming out of a tweeter, which are much more directional.
That's right. So on a typical direct radiating loudspeaker, which the one we're talking about is, at low frequencies, the speaker is, like, as you say, is omnidirectional. As the frequency gets higher, the directionality of the speaker gets narrower and narrower. Now, if you're measuring the speaker to tune it in an anechoic chamber, of course, you're only measuring what's coming directly from the loudspeaker, or you're measuring it, if you turn the speaker relative to the microphone, you're measuring it at discrete angles around the loudspeaker. In a room, that speaker's direct sound, the first sound you hear comes directly from the loudspeaker. Early reflections are the second sounds that you hear. And if you think about it, a typical setup of a speaker in a room, the speaker, if you're sitting in front of a stereo pair of speakers, the first sound you hear coming, let's say we're talking about the left speaker. The first sound you hear comes directly from the loudspeaker. The second sound you hear comes from either the sidewall or a combination of the sidewall and the floor. They're typically the closest objects, and the back wall. Of course, the back wall doesn't have much reflections at high frequencies because there's not much energy coming out of the tweeter around the back of the cabinet. But there is a fair amount of energy coming off the tweeter that bounces off the wall. But if you look at the angle of a typical stereo or even home theater setup, the angle at which the first reflection off the sidewall occurs is somewhere between 60 and 75 degrees off axis. So in theory, the second sound you hear comes, you hear what's happening at 60 degrees off axis. So
by the way, somebody in the chat room asked about the definition of the term off axis.
Well, on axis is when you're directly in front of the loudspeaker, so that the sound is coming off the baffle at right angles to the baffle. Off axis is any angle off of that, up, left, right, or down. So let's say we're off axis by 15 degrees left. That would mean that you're measuring it to the left of the center of the baffle at right angles. You've moved over 15 degrees in one or the other direction. So that's what off axis means. The on axis is the direct sound where the microphone is at right angles to the front center of the baffle.
Yep.
And in some cases, what I do is, or in all cases, what I do is I determine what the 0 degree measurement axis is. And on a towered loudspeaker, if you think about it, most people who sit in a chair, their ear is typically between 36 and 39 inches off the ground. That's for a normal height person. It does vary with different individuals, so you can't encapsulate one measurement or one number into all people. But in general, what I would do is I would do all of the acoustic measurements and tuning where the microphone was centered on where the ear would be when seated in a chair, which is typically 36 to 39 inches from the ground or the bottom of the speaker up to where it is. So in this case, the listening axis is not on the tweeter. It's actually just at the bottom of the mid-range driver, which is about 36, 37, I think, inches off the ground.
Okay.
So I hope that explains the on and off axis.
Yes, I'm sure it does.
So let me just keep explaining about the directivity and the dispersion. So what you need to really be careful that when the mid-range driver reaches the point where it's crossing over to the tweeter, the directivity of the mid-range driver, if the frequency of that crossover is not properly chosen based on the diameter of the mid-range crossing and the frequency at which it crosses over to the tweeter, you can actually have it so that at, say, 60 to 75 degrees off axis, the speaker actually has a dip because the mid-range driver isn't as good as dispersion at its highest frequency as the tweeter is at the lowest frequency it produces, which in this case is the same frequency that they're commonly producing as the crossover transitions from the mid-range driver into the tweeter. So if you measure that speaker that is improperly voiced for good balance far off axis. And what that means is you have to drop the crossover frequency of the tweeter such that the tweeter's directivity is the same, or as close as you can make it practically without crossing the tweeter over so low that it blows up. So you want to balance off power handling with directivity and the crossover point between the mid-range and the tweeter, so that as the mid-range driver gets larger, the higher frequencies become narrower and narrower. So you've got to choose the right frequency for the size of driver that you have, and then try and get the tweeter to go down that low and still have the dynamic capability and low distortion, so that the directivities are the same where they are crossing over. And that really gives a result especially in a reverberant or reflective room where their sidewalls in particular are reflective, will make the speaker sound much more smooth. Speakers that aren't voiced that way can have a tendency, even though they're flat on axis, can have a tendency to be very bright, very harsh. And so this is the kind of nuance that I think a lot of loudspeaker designers can hear, but sometimes they don't understand what this phenomena that's occurring comes from.
Mm-hmm. Well, you mentioned also another goal that you and every other speaker designer has is low distortion. And
That's right.
I know that you worked on the woofer and the mid-range of the T3 of this new speaker from the ground up. Basically, you redesigned them for these speakers in order to achieve low distortion. Tell us a little bit about that.
Well, using some of the computing power of computers today and software that's available, finite element analysis is becoming much more practical to use. And in this case, we were able to minimize the nonlinearities of the movement of the cone, or the distortion that's created by the nonlinearities of the magnet structure of a typical loudspeaker. I think you've got an image showing the FEA analysis of the magnet structure of this woofer and mid-range driver.
Yes, it's called T3 magnetic field. There it is.
There it is. So what you see here is a slice or a cross section of the magnetic structure, and
of the woofer we're talking about here.
And the mid-range has the same. It's just it's just a different scale.
Got it.
But just proportioned up. It's scaled up for the woofer compared with the mid-range. But what you see here is one of the phenomena that causes distortion, and in this case, it's pure second harmonic distortion, is the first, let me describe what you're looking at. The two square blue squares on left and right side are the actual magnet. And many of you have seen a ceramic magnet, and it looks like a donut. So that is the outside ring sliced in half. So you see the magnet is the two blue squares. The large yellow sort of L-shaped part is the actual backplate / pole piece combo. It's actually a single forged piece of steel that, of course, it's circular. All we're seeing is a cross section of it. Mm-hmm. So that, and then that small rectangular piece on top of the blue squares on the left side and the right side are what we call the top plate. So you see these lines that are traveling around or moving around. Well, they aren't moving, but that's what they do, is that this is the magnetic circuit that's created by this magnet structure. And one of the phenomena that's we're trying to control here is the non-symmetry that you get by putting all this magnet steel behind or on the bottom of this image, but on the top of this image, if it were just a flat pole piece, you would actually see the distribution of the lines that jump that little gap between the small rectangular and that L-shaped device, you'll see the lines are very evenly spaced, both in the middle and on top and bottom. And what that results in is that when the voice coil, of course, the voice coil is sandwiched in between that area where all those little lines are concentrated. And what happens is the voice coil, when it's moving up versus when it's moving down, it means that the force remains the same on both sides. If it is not symmetrical on both sides, you will actually find this is a source of pure second harmonic distortion. So we've been able to really reduce distortion by creating a structure in the steel of the pole piece / backplate. And you'll notice it's got kind of a unique shape. It's sort of not straight up, and it has like a radius on the top. And all of those features through finite element analysis allow us to get that concentration of magnetic lines really focused in the gap so that the pure second harmonic distortion that's created by this non-symmetry is reduced dramatically.
Now we have another graphic to show, just to show the difference between a conventional design and this design called the graphics called T3 symmetrical drive, and we should see that. Here we go.
So the one on the right is the one that we've been just talking about, and this is only one half of the circuit.
Yep.
And then the one on the left shows a typical pole piece. And if you were to see the magnetic lines on the left-hand image, you would definitely see that they're not evenly spaced throughout the gap and on the above the gap and below the gap. And of course, that number 1 there is what I was trying to describe earlier, is where the voice coil sits. And that number 1 feature moves up and down. And of course, where the 1 is, the circle there is that's where the cone starts to attach. And so of course it comes up, and that's what pushes the cone in and out.
Exactly. Okay. So I just wanted to make sure we saw the difference between a conventional design and this design that you're talking about, which leads to lower second order harmonic distortion. And lower distortion is always a good thing. I couldn't agree more with you on that one.
Now, there's another feature we include in this design, which we call it's a common technique used in other magnetic applications, and it's called a Faraday ring. And one of the phenomena that occurs in a loudspeaker, when you have a coil, which is the voice coil, it actually can be defined as an inductor, which has reactance, which means its resistance or its impedance changes with frequency. So an inductor, as the frequency gets higher, the impedance gets higher, the resistance that pushes back gets higher. So when you have inductance in a voice coil, that's okay. But what happens with a loudspeaker, the voice coil is moving up and down. So when it moves up and down, the inductance or the frequency-dependent resistance of the coil actually changes at any given frequency. So that when it's up, it's one inductance, and when it's in the middle, it's another inductance, and when it's down below, it's another inductance. So as it's moving in and out, its inductance is modulating, and that's not a good thing, because it is the source of pure third harmonic distortion, or odd harmonics, because of the nature of the way it, like with the non-symmetry, you have in one direction it distorts one way, in another direction it distorts another way, but in the inductance it modulates. So from the rest position, it modulates inductance being lower in one direction and higher in the other direction. That's a source of pure third harmonic distortion. And Faraday figured out that with an inductor, and it's used in other applications, not just in loudspeakers, in lots of other magnetic and electronic applications. If you apply this to a loudspeaker, And how we do it is we put a copper cap on the top. It has to be a non-ferrous material that is inside the coil, which in this case, if we were to put a copper cap on the top of the pole piece, that's that part we showed earlier, which has that unique shape to create the symmetry of the above the plate and below the plate of the magnetic lines.
Mm-hmm.
But we also put a copper cap on top of that, so that the voice coil actually has what we call a shorted turn internally. And when you put a shorted turn inside a coil, the inductance goes away for all intents and purposes. So that now, when that voice coil moves up and down over a piece of metal, the inductance barely modulates. And so that basically gets rid of third harmonic distortion.
Extremely clever.
Just a little bit of a lesson in second and third harmonic distortion in dynamic drivers.
Right.
There'll be a test on this later on. Okay, so
pay close attention. A couple people in the chat room have been asking about the driver complement. When we looked at the original speaker, the family of speakers there, the towers look like they have 3 or 4 drivers. Here it is, sort of 4 drivers plus a tweeter there. A little harder to see, but it's certainly there. And you call this a 5-way design, or a 5-way transitional design. Tell us how that works.
Yeah, well, I came up with a 5-way transitional, for lack of a better word to describe it. I don't believe it's been called that by anyone else before, but if you put up the cutaway of that loudspeaker, I think I gave you an image of that.
You did, called T3 cutaway. There it is.
There it is. So now you can see what's going on inside. Let's just talk about the 3 woofers, the 3 drivers at the bottom of the cabinet. Mm-hmm. All 3 woofers produce the lowest frequency together, so that they produce the deep bass as a trio. But as the frequency
in fact, the radiating area of those very low frequencies is the sum of the areas of each of those drivers, right?
That's correct.
Okay.
In fact, there's a little bit more, because it's hard to see in this thing, but if you look, you can see it. You'll notice the drivers have a trim ring around them, which is actually horn loading the driver just a little bit. And that actually puts a bit more loading on the driver, but the actual surface area of the driver appears or performs to be bigger than it really is, because it's actually loading a little bit into that flange. So that was just another little tweak that we wanted to do to try and enhance the output capability of the speaker. Of course, it does load the driver a little bit more, but that's all part of the equation. So that's just a minor point. The main point is that, as I said earlier, all 3 drivers produce the lowest frequencies together as a piston. And I found that by spreading 3 drivers over a larger area, as opposed to having this single driver with the same surface area, the output is actually the speaker actually goes down deeper in bass, because it couples more efficiently into the airspace that's around it. So just switch back to that again, if you could. So the 3 bottom woofers, they, as I said, produce the lowest frequencies together. The lowest woofer, the one closest to the ground, only goes up to about 100 hertz, and then it rolls off. The next driver continues up to about 250 hertz, and then it rolls off. And then the next driver travels up to about 500 hertz, and it's the only driver that crosses over to the mid-range driver. And then, of course, the mid-range driver crosses over to the tweeter. So what is actually happening is that at the very lowest frequencies, the source of the sound is quite large, much larger than even a 15-inch woofer. As the source gets, as the frequency gets higher, the source gets smaller and smaller and gradually smaller and smaller and smaller until it gets to the tweeter. And that's a good thing because it gets rid of any interference between drivers that are producing common frequencies that are related to the distance they are apart as a function of the wavelength of the frequency they produce. So that it's actually well thought out in terms of making sure that nothing gets in the way of anything else. And it's almost like it's a source whose size changes as a function of frequency. And that's a good thing.
Yeah, that sounds great. M5 in the chat room is asking, it looks like the displacement volume on the lower three drivers is not the same. Is that correct?
Well, if you look at the bottom opening or let's say the cavity, each of those woofers is in its own enclosure and each has its own port. And the lower cabinet, you'll notice if you kind of visually see, it's about the same amount of space as the middle cabinet opening, but the top one is a bit smaller. But if you just scan a little bit higher on that image, you'll see that in behind the mid-range driver, there's actually a wall. And that little extra space up and behind that wall actually is shared by the top woofer because there's a hole in that brace that's dividing them.
Got it.
So that the volume of air in the top woofer is the same as the middle woofer and the bottom woofer, even though it's not the same shape. At those frequencies, though, the volume of air works as a lumped element. So, it's just high and low pressure changes inside. So it happens everywhere at the same time. And then, of course, the mid-range driver is housed in its own enclosure. And, of course, the tweeter doesn't need its own enclosure because it's a closed-back tweeter, only exposed to the outside world on the front. You'll notice there are three crossovers in the system. The bottom crossover, as you can see by the wiring, it just wires direct to the bottom woofer. The middle crossover drives the middle woofer and the top woofer, and the top crossover drives the mid-range and tweeter. One thing that we talk about, and we can leave this image up to describe it, is along with one of the challenges of any loudspeaker is how well it integrates in a room. And the rooms usually have some issues, or many rooms have some issues at low frequencies where the wavelengths of the frequencies are somewhat proportional to the room's dimensions, so that you get all kinds of reflections, standing waves, etc. And basically in a rectangular room, square room, whatever, you get three fundamental standing modes, length, height, and width. Placing a speaker in a room, and then where you are in the room and where the speaker is with respect to the boundaries, and of course where you are with respect to the boundaries, all play a role in what the acoustic event that you hear coming out of the loudspeaker sounds like. And I found that a little bit of adjustment with the loudspeaker, sort of fine-tuning it for its position relative your position or the speaker's position in the room, makes for fairly good productive experimenting to actually kind of tweak the speaker. And we include with this speaker some what we call plug ports, or port plugs, plug ports, so that you can actually dial in some minor modifications to the frequency response of that speaker in its particular position or whatever particular room. And I invite people to sit down and, listen and do some modifications. The fact that the ports are in different locations relative to the floor and ceiling and any position for that matter, plugging one or the other might give you a different result, even though it's plugging the same volume of air and theoretically should be the same. And in fact, when you measure it in an anechoic chamber, it is, but the anechoic chamber, you have to remember, is totally absorptive, so that reflections don't play a role in that environment, whereas in rooms they do. So just being able, and I think there's an image there showing the terminal and the port with the port plug in it.
Called the binding, it's called T3 binding posts. There
right,
it is.
So there you see the bottom woofer port tube, and we, in this case, took a picture with it, the port plugs plugged right inside.
Mm-hmm.
And then, of course, the bottom three means that you can actually tri-amp or tri-wire this loudspeaker. You can even put a jumper on the bottom terminals and disable the bottom woofer in rooms that are way too bloated. And that bottom woofer actually becomes an active absorber, because when you short it, the voice coil is engaged, and when it moves, the voice coil generates heat. Those are minor adjustments, but in the high-end community, when I hear people talk about nuances that they pay a lot of attention to when it comes to things like the difference between a 96 kilohertz source or a 192, man, if you can hear those things, then you can definitely hear differences in the way I've described the tuning of this loudspeaker.
A couple quick questions from the chat room. One is SSB 201 is asking, what kind of tweeter is it? Is it a dome, a ribbon?
Yeah, it's a 1-inch dome tweeter made out of titanium. And the beauty of this tweeter is it's one of the most sensitive 1-inch dome tweeters on the planet. At 1 watt going into that tweeter, it produces in excess of 96 dB.
Wow.
And at 1 meter. And that is very sensitive. It has a fairly... and it even has a heat sink on it to try and dissipate the heat and maintain good stability when it comes to thermal stability. As you know, or may not know, as you heat up a voice coil, the DC resistance goes up, and so does the output goes down, so that it has what they call dynamic compression. And by making the speaker extremely sensitive, this tweeter never gets into dynamic compression, and it also allows me to cross it over quite low. So it's a tweeter I have had very good success with, and I must say I've been working to improve it over the years, and I just can't. It's really hard to do.
One other quick question.
Go ahead.
Sorry, from the chat room, Creamy Corn Cob asks, is there any damping in this ported design? And if so, what kind of damping material is used?
Yeah, we use the old school fiberglass, because fiberglass is there's damping all over this speaker. It's just that if I put the damping in, you wouldn't see anything else.
Yeah, right.
So maybe we should do an illustration of it before and after damping. Maybe that would work. But
yeah, maybe.
I use fiberglass because you know what damping does. And I use damping in the middle of the volume of air, not on the walls of the speaker. Because if you think about it, damping material will only damp air that's moving. But the air is not moving on the boundary of the speaker. It's moving in the middle of the air volume of the speaker. On the boundary, it's called potential energy. In the middle of the speaker, it's called kinetic energy. And the only way you can
moving,
the only way you can get rid of the standing wave is to damp it when it's moving. So that what happens when it's moving is that fiberglass is just all these little fibers that are all intersecting one another. And when the air is moving, those little intersections actually vibrate against each other. And if you do this long enough, even with your fingers, you'll feel it getting hot. Mm-hmm. And that's what happens, is it turns the acoustic energy into heat. That will not occur on the boundaries. It only occurs in the middle. And I find that fiberglass is one of the best materials for converting acoustic energy when it's in a kinetic environment of moving air to heat. And so, yes, we do use damping material inside the loudspeaker, and that's how we use it.
Right. Good. Control Freak in the chat room is asking, what's going on with those feet? And we're going to talk, we had a plan to talk about the feet on this speaker, but if you'll take them, hang on one second. Yeah, I know. We may not get to the other thing we were going to talk about today, which means you'll have to come back.
Yeah, maybe that's what we should do, actually.
I'm kind of thinking that. But if you'll give me just a moment, I would like to thank our sponsor for this episode, which is SmartThings. Now, let me tell you about CNET's highest-rated smart home system, which, of course, is called SmartThings. Now, SmartThings allows you to monitor, control, and automate your home from anywhere using your smartphone. A single app on your smartphone gives you complete control over your smart home. Now your lights, locks, thermostats, and home security are all connected through a single app. And you don't need a different app for every product, which I think is really, really cool. The intuitive controls allow you to set up rules for your smart home through their free iOS, Android, and Windows phone apps. With SmartThings, you can customize the way your smart devices talk to each other. So now you can tap, say, good night on your phone. The lights will turn off, the thermostat will adjust, and the doors will lock. You can set your lamps to brighten each morning at sunrise or when you wake up, which for me is long after sunrise, I will tell you. And you can even keep your home protected with SmartThings with home security, motion detection, water detection, and more. You can even enable your speakers, dig this, to broadcast the sound of dogs barking if there's motion outside the house. How cool is that? I love that. You can set up a camera to take a series of photos when unwanted motion or entry is detected. And you can have your doors recognize you when you are close and unlock themselves as you walk up. And big news for home theater owners is that Logitech Harmony has now joined SmartThings Labs, which is involved with integrating with different products. And Logitech Harmony is one of the most recent. You can now integrate your home entertainment system into your smart home and control and automate over 270,000 entertainment devices. Logitech Harmony is my favorite universal remote, made even better by integrating with the smart home system. Now you can control your entertainment system from the SmartThings app, as well as controlling SmartThings devices from the new Harmony Home Control remote. You could do things like automatically turn on the local news or weather channel when you wake up, have your TV turn on when you come home and turn off when you leave. I also love that SmartThings now integrates with the Sonos wireless whole home audio system as well, also part of the SmartThings Labs. You can configure your Sonos system to play a certain station or playlist when you open the door. It can even give you spoken notifications through the Sonos speakers. Very Star Trek, if you ask me. There are so many ways to customize your SmartThings home. And hey, SmartThings was named CES 2015 Editor's Choice Award by Time.com, the website of Time magazine. You really should go check out the SmartThings website. To get you started setting up your smart home right now, SmartThings is offering Home Theater Geeks listeners 10% off any home security or solutions kit and get free shipping in the U.S. when you go to smartthings.com/twit and use the offer code TWIT at checkout. And we thank SmartThings very much for their support of Home Theater Geeks. Okay, so I'm talking with Paul Barton about the new Imagine T3, and there's so much to talk about that we're going to save what else we were going to talk about for another show. But I think we should get right back to the question that was asked by Control Freak about what's going on with those feet of the speaker. And this is an important point that, Paul, I know you wanted to talk about. We have the photo called T3 Spike. There's the spike. So that's your basic spiked foot. Tell us a little bit about why speakers even have spiked feet.
Well, often, well, in this case, it's a towered speaker. It's about, it's over 3 feet tall or close to 4 feet. And in order for it to be fairly stable, it's kind of nice to put it on something that can maybe go through the carpet and find its stationary on the floor. There's a school of thought, pro and con, for using spikes in different ways. We'll talk about that a little later because I think we've given the end user the ability to experiment in different ways with the spikes. Number one, though, is that it keeps the speaker fairly stable from falling over. What we've made this out of is those are all CNC machined solid aluminum out of aluminum rod. And you'll notice the edges are all diamond cut beveled. The bottom plate is solid, made of solid aluminum, machined on CNC. So it's a fairly robust base, totally adjustable and lockable. There is another image that you can put up that shows the option that can be used along with it, and that is something we call simply the puck. And if you look closely underneath the spike, that dome piece actually has a 80 durometer rubber insert ring underneath, so that it actually acts as somewhat of a shock absorber, so that the spike so that the spike actually sits in a little bit of a divot inside the puck and allows the speaker to be somewhat decoupled from the surrounding. A lot of people would be resistant to also putting that spike on a hardwood floor, which can damage it. So using the puck in those cases might be desirable.
Now, wait a second. Hang on a second. A couple people in the chat room are already talking about what I wanted to ask you. Beard57 says, the feet have spikes on the bottom where they meet the floor, so it's difficult for vibrational energy to transmit into the floor. And this is what I always believed too. Is that correct?
No.
What?
No, the energy will transmit. Like, where does the energy go? Like, energy can't be created nor destroyed. So if the cabinet is moved, it can only be changed from one form to another. So if the cabinet vibrates or moves, there is energy in that movement. So that energy, the only way to get rid of it is to turn it into another form of energy. Or you can keep it the same, keep it in vibration, and it just travels through the medium that it's vibrating and carries on.
So in the case of a spike, if the speaker cabinet is vibrating, that vibration is transmitted through that spike to the floor, and the floor carries it away.
Well, if anyone thinks that the spike is stopping energy from flowing into the surface it's sitting on, could they please tell me where the energy is going that's not going into the floor? The only other, it has to turn into, what does it turn into? It has to turn into heat, or it has to turn into something else being vibrated, or maybe it gets turned into light. I don't know, but it's certainly
probably not.
No, probably not. But just in pure physics, that's something that a lot of audiophiles kind of resist coming to grips with, and that is pure physics. And so, but let me just explain the reason why we put different features in, because I want the avid audiophile who thinks that the spike is decoupling it to just have a listen to what I'm saying. If you have this spike, say, on a normal floor, and where I live, the floors in my living room are hardwood floors that are basically 6 by or 8 by 2 beams underneath. So when I'm sitting on my chair in the room and a speaker is playing, and it's coupled hard to the floor through, say, a spike or just on the speaker itself, the acoustic event that occurs in the loudspeaker comes from the speaker and travels through the air and gets to you at the speed of sound in air. But any vibrations that transmit down the cabinet into the floor it's sitting on, whether it's through spikes or not, and the spikes won't stop any of that energy from going through them unless it's turning it into heat somehow. So that now the energy, that the acoustical event that the speaker is producing travels through the cabinet, down through the spike, into the floor, through the floor, up your chair till you feel it. But that happens faster than the sound traveling in the air, because sound travels through a solid faster than it travels in the air. So my question is, which one is better? Do you decouple it using the puck that I've given, or do you rigidly attach it so that you actually feel that kick drum before you hear it through the air? Is that right? I can tell you it's different, and maybe that's what people hear, is that difference. But when you do something, I always get a kick out of audiophiles who do something to a product and it always gets better. It never gets worse.
All right.
Think about that.
Hmm.
You know,
Well, hopefully there are some audiophiles out there who will try something, and if it sounds worse, they'll notice and acknowledge that.
Well, I've never seen anybody say, "Oh, I put a Kleenex in front of my speaker and it sounded terrible." No, they put a Kleenex in front of the speaker and they go, "Yeah, that made it sound better."
You know, that actually happened with the Yamaha NS10.
I've seen studios set up.
Actually, put a piece of Kleenex in front of the tweeter. Anyway, getting back to these pucks and the spikes, which, by the way, I think that you should call that the spuck.
Right. We'll call it the spuck. That setup where you see it on the puck, we'll call that the spuck setup.
There you go. I like it.
Okay. But in this case, where the picture you're seeing on the screen, in that case, that is actually discouraging the energy from going into the boundary. That 80 durometer rubber is actually quite compliant with that weight on it, and it actually makes the speaker kind of suspended. But I invite anyone to kind of, if they're really into it, to do some subjective blind screen evaluations comparing with and without those spikes, and make sure you do it without knowing which is on the spike or without.
Just put blind testing is a whole nother topic we could spend another hour on. Yeah. Easy.
Just put a piece of black cloth around the bottom of the speaker and get your wife to tell you, put it on the spike or not, so that you go in and you listen to it. You don't know whether it's on spikes or not, and you determine whether you think it sounds better or worse or different.
Very good. Okay, in the time left, which isn't very much, let's talk a little bit about tri-wiring and bi-wiring and bi-amping, which you've allowed, as you mentioned earlier, with this speaker. If we take a look at the picture called binding posts, we will see that you can actually drive each, well, not each of the drivers. You've got 3 pairs of binding posts there, right?
Yes, and I think I mentioned earlier, the bottom pair drives just the bottom woofer. The middle pair of terminals drives the 2 middle and upper woofer, and the 2 top connections drive the mid-range and tweeter, so that you can actually have an amplifier driving the bottom woofer, a different amplifier driving the middle and top woofer, and a different amplifier driving the mid-range and tweeter. And of course, people talk about bi-wiring versus bi-amping. Bi-amping is definitely the better, more demonstrable improvement. Bi-wiring or tri-wiring or bi-wiring is an incremental improvement, but not to the same degree that you could expect when you run. Think about it. You could run this T3 with 6 amplifiers. And in fact, you could even run it so that the mid-range and tweeter are driven by a tube amp, which is sweet and warm, and drive the rest of the system with the transistor amplifiers for the good, strong damping and low, high damping factor that transistor amplifiers have. Yeah. Solid state amplifiers have, and that gives you the best of both worlds. But one caution: if you don't use the same make and model of amplifier to drive each of the driver sets, bottom woofer, mid and top woofer, and tweeter mid-range, you must ensure that the amplifier gains are the same, because if they're not the same model, there's a good chance that one manufacturer hasn't chosen their amplifier to have the same voltage in, voltage out ratio. So you need to change the volume control so that your tube amp, if you wanted to use that on the mid-range and tweeter versus the transistor amplifiers, they may not be the same. Well, it's certainly not going to be the same model, because one's a tube, one's a transistor, but you've got to make sure that the amplifier gains are the same. Mm-hmm, and that's very easy for a technician to guide you on, or if you're technically inclined, you could do it very simply with a tone generator and a voltmeter.
Mm-hmm. Now,
Just
by amping, I understand. It's you put separate amps on each of those inputs, and they drive the different drivers, power the different drivers. By wiring is taking the output from a single amp and sending it to the different those different inputs on the speaker, so that they're all being driven by the same amp, but using separate wires.
Right.
What's the advantage there, if any?
Well, the advantage might be simply by tripling up on the amount of wire going to the loudspeaker from the amplifier. You're actually sending the signal to the speaker with less resistance, DC resistance. And that's a good thing. If you can have zero resistance in the wire from the amplifier to the speaker, that's a good thing, especially when the speaker's impedance is like ours, is a lower impedance. In this case, it's a 4 ohm, nominally 4 ohm loudspeaker.
That's important to know because not all amplifiers can drive 4 ohm speakers.
Well, more and more today with digital technology and especially with switching power supplies, you have lots of current capability. Amplifiers today don't have the same restrictions on impedance as it used to in the past. In fact, there used to be some of the brands would have a safety sticker on the back to say that this unit is not designed for 4 ohm loads, 8 ohm only. And it was only because safety insisted. I mean, they run at 4 ohms, fine, but they just get too hot because the current is higher when you use a 4 ohm load, and they may not have sufficient heat sinking on the amplifier to dissipate the heat that's generated by a 4 ohm load versus an 8 ohm load. That's because of digital switching's power supplies and many digital amplifier outputs. They hardly even have heat sinks. They don't get hot. So current's not a big deal as much as it used to.
Okay.
But the heavier the gauge wire going to your speaker, the better, especially when the speaker's impedance is somewhere in the range of 4 ohms. So think about this: if the wire going from the speaker to the amplifier is a half an ohm, that means that 15% of your is that 15%? Half an ohm and 4, yeah, it's about
12.5%.
12.5% of the energy is being dissipated by heat in the wire because of its resistance. So yeah, keep that resistance low, and if by wiring and tri wiring, and it will reduce the DC resistance into the load, that's a good thing. But it's a low order effect, I must admit.
It's not that critical.
That's it's not that noticeable. It's very as long as it's decent wire, like as long as you don't use 32 gauge wire, which is about the size of your hair, then you're in good shape. But increasing the DC resistance, keep in mind, in fact, with this loudspeaker, the impedance of the crossover is very constant over its operating range just by virtue of the configuration of the system. And that's a good thing because it means that any DC resistance that might be in the wire or any lack of damping, let's say you were even driving it with a tube amplifier whose output impedance was quite high, you would find that the T3 is very immune to that because its impedance is very constant. And being very constant means that it won't become a voltage divider that is changing with frequency. And that can actually change the frequency response away from what I intended when I did the original voicing. So you don't want the amplifier's output impedance to be too high in any situation. And of course, tube amplifiers have higher output impedances. So a speaker who has a wildly changing impedance curve, like many of them have big peaks at the low end, and then they have a great big peak in the mid range. Well, you put that on a tube amplifier that has a fairly high output impedance, and you will find that the speaker's frequency response will tend to mimic the impedance curve. It'll change by virtue of the changes that occur in the impedance curve.
I didn't realize that. That's a very good thing to know.
And you'll often hear people who put tube amplifiers on a speaker that they've been listening to with a transistor amplifier. They go, "Ooh, as soon as I put the tube amp on, it sounded really warm. Well, of course it sounded warm. It's because its frequency response changed because the impedance of the loudspeaker has a bump in it. And that bump, that warmth will occur at the low frequency where the tuning of the box occurs.
Wow. I always thought that the warmth of a tube amp was because of the nature of the tube amp and of the second order or even harmonic distortion endemic to tubes. But you're saying it's as much, if not more, the interaction between the amp and the speaker.
Well, you just have to measure the frequency response on a tube amp with a speaker and then on a transistor amp with a speaker. And you'll see on paper what the changes that you're hearing. And it's because the frequency response is changing.
Got it. Well, you know what? We've come to the end of a fabulous hour, and there's much more to talk about, such as cabinet construction and so on like that. But
well, I had a lot more in mind, but I'm glad we could cover those in the kind of detail that we did. And before I go, I just want to introduce everybody to Kemar. In fact, Kemar is the mannequin dummy head or torso that we use to do headphone design. The M4U ones that I have on me, and Kemar has a pair of M4U2s. And he's actually wearing a PSB logoed Montreal Canadiens number 76 PK Subins T-shirt, hockey T-shirt, who endorses PSB.
Wow.
Whenever he gets a chance. So anyway, I just thought I'd introduce everyone to Kemar. You'll be seeing more of him in the future.
Good. Yes. Well, next time you're on, we're going to talk about headphones and more particularly in-ear monitors, which PSB will soon introduce its first in-ear monitors. So once those hit the market, let's get you back here and talk about that, because there's a ton of interesting things to talk about with those in-ear monitors as well. I'm sorry we ran out of time.
Well, yeah, just keep your eye open for a new PSB model called the PSB M4U, which stands for Music for You.
I didn't know. I never knew that. That's great.
Yeah, that's what it is. It's called the M4U 4. And I think they just popped up a little picture of it there. A little sneak preview.
All right. There it is.
Yeah.
And there's tons of interesting technology in these as well, but we've run out of time. So will you come back and talk about those another time?
Definitely. You just name the time. I'll be here.
Excellent. Thank you so much for being here. That's Paul Barton of PSB Speakers, and of course his website, psbspeakers.com. You can find me, of course, at avsforum.com. You can email me at scott@twit.tv. And you can follow me on Twitter at htgeekscott, also at AVS Forum. You can always find previous episodes of Home Theater Geeks right here at twit.tv/HTG, also on our YouTube channel, youtube.com/twithometheatergeeks. Next week, my guest geeks are scheduled to be Sean Olive, Brian McCarty, and Bob Schuline, all of whom are co-chairing a really interesting AES conference this coming weekend on the future of audio technology. So they're all three going to be here next week to talk about that conference, which I will be attending as well. So there's going to be a ton of interesting stuff to talk about then. So I do hope you will join me. Until then, geek out.